Good afternoon, everyone. My name is Manuel Gutierrez Lopez, and throughout the summer, I've been working on a project called Analyzing Complex Electrical Events, Amelia Hernandez and Glen Woodworth as my mentors. Give a small overview of my presentation. I'm going to start off with some background information, and I'm going to delve into the purpose of my project. I'll go through the research goals, the bigger picture, research methods, and then into the lessons that I learned, the conclusion that I drew off of this internship. An electrical transient event is a short, abrupt change in electrical system's parameters. Think like a spike in current or a drop in voltage. Transient events observed during the experimentation and modeling of this system were a three-phase bolted fault and a load step. A load step is a sudden change in the electrical load of a power system. Think of like a massive industrial machine being plugged in. A three-phase bolted fault is a short circuit between all three phases of a power system, with zero impedance at the fault location. This creates the worst possible fault conditions where the current is at its maximum. The top left there is a diagram of a three-phase bolted fault. When discussing inverters, two main technologies are referenced: grid forming and grid following. A grid following inverter matches its frequency to the grid, injects current whenever it's necessary. Grid forming inverter can regulate its voltage output to help the grid maintain nominal voltage and frequency values, or create a microgrid of its own. On the bottom part is the control scheme for a grid following inverter, and then under it is the control scheme for a grid forming inverter. The goal of this project is to create a method that breaks down how an inverter reacts during a transient event, and then use that information to compare computer models of inverters to real inverters. On the top left is a part of a grid design in Power Factory. And under that is a solar farm that was designed in PSCAD. These are the two models that we're going to be using to compare with the PCS 100 energy storage system on the right. That's the inverter that I'm going to be referencing throughout this presentation. Now, with some background information, you could look at these data sets and split them into a period where there's a spike and a period of decay. But visual identification is not enough. You need a mathematical approach to be able to quantify each segment. Then use these segments to compare the models to real inverters. Look at the graph. That is the average voltage graph for the Power Factory model. And under it is the same graph, but after the code ran, segmented it into a large spike in the beginning, and then a period where it's not quite at baseline, but it's definitely not a spike. The last line is the start of the steady state. Now, that's there as a visual aid. We're not really going to be using it as a comparison. When creating an electrical system that satisfies the requirements for a design, lots of testing is required. This testing is time-consuming and expensive. Modeling gives engineers more flexibility in the development process, allowing them to make as many changes, work on as many ideas as they want to, with little or no hassle. However, an issue arises when a power system analysis software shows itself to be unreliable. If the results that the model gives you are flawed, the whole design is in jeopardy. When I started this internship, I first worked on understanding root mean square error. Root mean square error is the industry standard metric used to compare model accuracy. The smaller the root mean square error, the more accurate the model is. The issue with this approach is its sensitivity to scale and its propensity to create misleading results. Researchers need more options. A model could correctly simulate the overall shape of the transient, but have a large magnitude disparity. This creates a misleading root mean square error calculation. Outliers in the data can also skew the result due to it squaring the difference between them. So a model could model the response well, but have one big mistake, and that mistake skews all the results. Because root mean square error is the only way that researchers can compare model accuracy, there's a need for more options that can excel in different areas. This project addresses that issue by providing a different way of comparing simulated and experimental inverter data. With that, researchers can improve the models to more accurately simulate real-world behavior. Improving a model could be a massive step forward for Alaska's microgrid-reliant energy infrastructure, paving a way for new microgrid projects or integration amongst existing microgrids. I started off by investigating related research papers, textbooks like this one, try to find a heading. Afterward, I used the bits and pieces I gathered from these resources to create a plan, and then that plan was translated into code. A key challenge I faced during this project was the extensive trial and error needed when balancing the sensitivity of the logic. The debugging would mostly entail following a specific data point throughout all the code, figuring out why it flagged, why it didn't flag, and then repeating this process for any number of those 500,000 samples. Key things I would change or do differently. At times, there was many ideas being worked on, and I would flip-flop between what I was working on throughout the day. This led to a lot of readability issues. So I would have liked to have made the code more modular and make it easier to read to avoid all those headaches during development and make adjustments much easier to make. As for advice, I'd say take a second to visualize what you're coding. Making diagrams and working out equations make a quick reference and get you out of a bind. It also helps catch any inefficiencies in the code. At one point, I made a convoluted and roundabout function to find basically the derivative over an area. And showing this function and discussing it with Glen, he pointed out the issue, and then we worked out a simplification. I applied that simplification to make the function faster and easier to understand. What were some successes? As a success for the summer, I developed a method that identifies sub-events in inverters during transients, classifying them into an initial surge and a return to steady state period. Each of these events were organized into a two-dimensional vector, one vector for each model for each event. Metrics inside of the vector were the duration of the event, the energy of the event. The energy of the event is calculated by finding the integral across the duration of it. This project showed me how flawed these models are and the importance of improving them to facilitate the engineering design process. On the left there is the current graph for the experimental inverter, and under it is a PSCAD graph. The PSCAD and the Power Factory one both did the same thing. They went out of baseline, they recorded a spike, and then they went back to baseline. We can see that in the experimental version, there's actually a recovery period where, while it's not a spike, it is still returning to a steady state. These are the types of assumptions that the models make that make the engineering design process difficult. Of all the things I worked on during this project, I think debugging MATLAB code was my biggest gripe. As a novice programming in MATLAB, the error messages I'd get were sometimes overwhelming, and at times it's difficult to know what to do with them. So a lot of Googling and help forums got me through them, and by the end of it, it was less of a hassle, much easier to deal with them. The most enjoyable aspect of my research was finally being able to apply my knowledge of electrical engineering and math to solve real-world problems with real stakes. It's fun to learn about these topics, but being able to use my studies to make progress is another level of satisfaction. Thank you. Any questions?
Hi, thank you. That was fun. My name's Michelle. I'm in the Anchorage office. I'm curious what the next steps to keep this going further are, and are you going to be working on it, or is somebody else taking on that work?
Well, while I will not be working on it, there are some next steps. The directly next step that you could take is finding a way of comparing these vectors. That's the main issue right now.
Cool, thanks.
Do you prefer Power Factory or PSCAD? Which one?
Oh,
Okay.
You can actually look at a couple here. So on some of them, they were very similar, but on a very, but point is, Power Factory definitely made the more egregious errors, for sure. Yes?
What other metrics did you think about or try using other than the root mean square error?
So that's the issue that we're on right now. That's where the project is, right? Because the segmentation is there, so we already have the events, the particular events. Now it's just about pairing those events in whatever way you want.
On that bottom graph, it looks like the search was under 0. What is that?
The surge goes under 0. No, it goes straight to 0. Yeah, it just goes straight to 0. Yeah.
Some of you in Glen's talks, and can you talk a little bit about how maybe it was interesting that there was terminology that you were able to sort of formalize in mathematical, in a mathematical sense, like, like what a good fit is or something. Is that was there new mathematical terminology that you are now applying to intellectual
No, I can't say there was some new terminology that we made for this. There was a lot of flip-flopping with the names for the initial surge or the spike or all this, which we then ended up on initial surge and a return to steady state or a period of decay. But that's the terminology we settled on.